Hey guys, this device may look familiar to some of you that have watched my older videos. What this is the guts from a Cardmatic Model 121 tube tester. I was perusing eBay and I saw that somebody was selling the guts out of one. And it got me thinking, I just might want to keep my eye on this in case I'd like some spare parts for mine. It also got me thinking, it's long overdue for me to service mine. I got it, I think about 2 or more years ago, and when I got it, it was in very good condition. It worked. It comes with a calibration card. It passed all the tests, and it seemed to be working fine. However, more recently, I've been finding more and more tubes testing bad. So much so they got suspicious, and I put those tubes into my Hickok 600A, which I have serviced and calibrated, and they tested good in that tube tester. So I want to take a look inside of mine, and also my power cord is kind of very frayed. I want to replace that. Now, I did get all the service info with mine, including a schematic and parts list, and it seemed like it was made with some fairly reliable parts. No tubes inside, like some of the older Hickoks. They would need to periodically be replaced. So, yeah, this is the first time I've ever actually seen the insides of one. I was not expecting to see a giant light bulb. Occasionally I've put cards into mine incorrectly and something lit up inside. There's a little red jewel overload indicator. No idea there was a gigantic light bulb behind it. I bet that's in series with the line cord and acts like a dim bulb tester to protect the device from overload. And if those are the original caps, in other words, if I have caps like this in mine, I should definitely check those and probably just go ahead and replace them because those are old electrolytics. Looks like this one has seen some work. It's a modern cap. Looks like a newer cap too. Let's see what else there is. Huh. Well, that's certainly different. I know there's no tube inside of mine, or at least the service info says there isn't. And now that I think about it, man, mine looks different on the front. These controls are all the same, but mine has 3 holes in it for inserting a small screwdriver for the calibration. And there's certainly no VTVM0 set control. Huh. Maybe this is an older revision of it. So maybe it wouldn't be so suitable for spare parts. Well, anyway, I'll get mine up on the workbench and pop it open and take a look inside. I just so happened to get a full complement of documentation with my Cardmatic tester, and that includes parts list and a schematic. And I was right. There is no 12AU7 in this. There's no tube in this at all. So now I'm really puzzled about that Cardmatic chassis that's on eBay. I got to figure it's somebody modified it. Either that, or maybe there was an early version of this that used a tube. I don't know. I'm not sure what they would have used it for, because this doesn't have transistors. It just doesn't need one. What it does have is a bunch of diodes in it, though. And see, there's a couple up here, and a couple more over here. I think there's a protective meter, and a couple more over here. So maybe before these diodes were available, an early version of this, they had to use a 12AU7. I don't know. Well, like I said, somebody might have modified it. Alright, so as I just pointed out, a bunch of diodes like 1N34s. And there are definitely some electrolytic capacitors. And then a bunch of resistors. So, if this is all original parts, I would not be surprised if some of these resistors have drifted off a bit, and if some of these caps are leaky. So, now, let's a matter of getting this open. I just went ahead and cut off this cord, took the top of the box off, took all the cards out, and then I proceeded to take all the screws off here, like I think I had tried doing once before. And it seems to loosen up each of these sections. They're still wired together, and so I explored further, and I think the way to really do this is I can put these screws back in and take the card tray out and remove the screws down here, and there are also 3 on the back of the case, and I think this whole assembly will pull out. Okay, so it turns out that you shouldn't touch any screws in the top. Remove the card tray, take out these 3 screws, take out the 3 on the back, and the whole thing just pulls out. So here it is. Big old light bulb, 150 watt GE. And it looks like it's all original. And there's no 12AU7. Now, one on eBay, it was mounted down in here. So, only 2 things I can think of is either there's an early version of this that had a tube, or maybe a later version, or somebody modified it. I did a quick Google search on Hickok 121 12AU7, and I didn't find anything about a modification, or any mention other than just people testing a 12AU7 with this tester. Alright, so you can definitely see you got 4 old electrolytics up here, any one of which may be bad. Got it's really probably a paper cap inside of a plastic tube, could be leaky. 2 smaller valued electrolytics, and a bunch of carbon comp resistors which may have drifted off of value. Let's see, and this guy and this guy I believe are selenium rectifiers. So 1 germanium diode, neon light bulb. There should be some more diodes probably buried down in here. Yeah, I can see there's the ones on the meter. Here's the card mechanism. So inside here is a whole bunch of spring-loaded pins. And when you slide in a card, the pins go through the, where there are holes punched out and connect up the right filament voltage, right bias voltages. You see those, all these resistors here forming a voltage divider, so it picks the right tap on there for the tube under test. And check out this transformer. All those taps. So many taps, I'm thinking that can't just be for different filament voltages. There's probably taps for both filament and plate voltage, or maybe grid voltage. Well, I can verify that because I have the schematic. Oh yeah, now I remember how this transformer works. I think that might be all filament voltages, but it's crazy. There's a whole bunch of taps with 10 volts between the taps, 1 volt between the taps, and 0.1 volt. So like I think for a 6.3 volt tube, it would take 6 taps here and 3 taps here. So say go from the top of this and then go down 6 positions to get 6 volts, and then go down 3 positions here to get 0.3 more. Whereas in a normal tube tester, say you've got 10 different filament voltages it supports, would be a 10 position rotary switch, 10 taps on the transformer. But this, it's almost kind of like a computer where you have to build it up by the 10s, the 1s, and the 0.1s to get your right filament voltage. Downside, of course, is you have to have so many taps in that transformer. And here are one of those resistor chains. They call that the self-bias resistors. And the other chain is for meter shunts. Well, I guess I'm just going to go through and test everything. So I will disconnect one end of these caps. I'm going to replace them all anyways, but I'm curious to see if any of these are bad before I do. Likewise that, and these two guys, hopefully I've got replacements on hand, otherwise I'll have to make an order and check on this. Okay, first let's check out the Astron 0.5 microfarad 200 volt paper cap. At least I presume it's paper. Alright, so check for leakage first. You want to know it actually, well, no, it does have leakage. Not much, but it does have leakage. And as for the capacitance, just check that for the heck of it. What range do we want? C1. Capacitance is actually right on about 0.5, but it does have a bit of leakage. So that's going to go. Now I'll check out some of these electrolytics. Alright, it should be 20 microfarad, get up to 250 volts. And let's see. So electrolytic position, and actually does not have leakage. I figured these caps couldn't be that bad, because this tester seems to work fairly well. But just the same, while I got it open, might as well. And capacitance, not super accurate at this end of the range, but it's opening pretty solidly, somewhere around 30 microfarads, let's say. Now I'll check out the rest. This cap tested okay as well, but not so much this guy. Got the leakage light on solid, and only 41 volts across it. Should be good up to 150 volts with no leakage. So for sure that one should be replaced. Not so fast. I can't test this one, not with that device anyways. 1000 microfarads, which is well in excess of the upper range on that device, but also it's only 6 volts, which is far less than even the lowest range for leakage test on that. Now I could use something like a modern multimeter to test the capacitance, but I don't have a device to test for leakage. I suppose I could hook it up with something like this on a microamp range in series with like this variable power supply. In fact, what the heck, why don't I go ahead and do that? Something I haven't tried before. That's really all that this is, a leakage capacitor is doing. It's applying a voltage to the capacitor and monitoring the current that's flowing through it. Once it charges up, that current should be 0 or very close to it. Okay, here's my setup. DC power supply, dial it into 6 volts. And that is going through this multimeter in the milliamp mode. And then I've got this in DC volt mode across the capacitor. So it's going to charge from this power supply through this ammeter, and we can monitor the voltage directly across the capacitor. So ideally it goes up to 6 volts, 0 current. I also threw a 100 ohm resistor in series just to limit the current when I turn this on so I don't overload my ammeter. Alright, so pretty quickly got about 5.8 volts, but I got a milliamp of current. That's pretty substantial. I don't expect it to go to 0, but it should be considerably less than that. Drop down to the microamp range. By way of comparison, I can take a modern 1000 microvolt or microfarad capacitor rather, and check out what kind of leakage current it's got. something to be careful of too is that ammeters add series resistance to the circuit. So notice that when I'm on the milliamp range, at 5.87 volts, at a microamp range, this voltage actually goes down because this has a larger resistance internally on the lower current ranges, so we're not quite seeing things right here. But what you can do to compensate is simply turn up the voltage in the power supply. So you want to get that to 6 volts. A little bit over. And that's not a perfect science. We need to get to 6.00 volts just in the ballpark. So we've got about 0.6 milliamps of current still flowing through this. It's still dropping, and I imagine it will for quite some time. Now, I use this tube tester on a regular basis. I'd say easily once a week. So it's not like it's been sitting around for 50 years and the caps need to really form up. Alright, so settling in at about 0.6, let's say. Alright, now I'm going to dig out a modern cap and check out how it performs. Well, as luck would have it, I don't have a 1000 microfarad cap on hand, but I do have a 470, and it's not ready for 6 volts, it's ready for 25, so I'm not exactly comparing apples to apples, but this should have considerably less current. And see, look, it's already down to 15 microamps, 10 microamps, and the voltage is considerably higher. Down to closer to 6. So we're looking at 2.4 microamps, considerably, a couple orders of magnitude less than the old vintagey cap. Now, in this particular application, does it matter? Well, probably not too much. I mean, considering they have a 100K resistor shunting it anyways, so there's going to be a path for DC to go around here anyways. But while I've got it out, it seems to be fairly leaky. I'm replacing the others. I might as well go ahead and replace it. While I'm at it though, let's do one more test. It's a 2200 microfarad at 16 volts, so closer in voltage to that, but more than twice as much capacitance. So let's fire this power supply up again. Overloading a bit on the current briefly while the cap's charging up. And dropping. Already much less current than that old cap had. But much larger capacitance. I've got a 100 ohm resistor in series with it, so it's going to take a bit longer to charge. We can see this is quickly settling down. Be less than 10 microamps pretty quickly, and we're at right about 6 volts. So, if you have the time and the patience and you want to check for leakage in old caps, you don't have something like this, or it's outside the range of this, you can rig something up like this if you've got a couple meters lying around and a DC power supply. Just measure the leakage current in the cap with a DC voltage applied to it. I thought some of you might be interested in seeing how this capacitor would fare with a modern ESR analyzer. So, got one here. Turn it on. 1000 microfarad cap. Should be way up here. 0.1 ohms ESR. And then these little test probes it comes with aren't exactly conducive to large axial caps. They're meant for surface mount caps, so I hooked up a clip lead to the negative, going over the negative side of the cap, and now I'll hook up positive. And we're at about 1.25. Now keep in mind, these do not test for leakage at rated voltage. These are checking for equivalent series resistance using a test frequency of usually 100,000 hertz at a few volts peak to peak. This is meant for testing capacitors using things like switch mode power supplies, where you're running at high frequency, a lot of current going through the caps. They are not, it's not testing caps that, as they would be used in a 60 hertz, 120 hertz type power supply ripple filtering application. So really not something you want to be using to test caps like this. Great for modern surface mount, small stuff used in modern solid state electronics. Use something like this, or make your own rig for checking the actual leakage at the actual rated voltage. While I've got this out, let's test this cap. 40 microfarad, 150 volt, very leaky. Again, hook up the ESR tester. Let's use the 47 microfarad column. Go up, 0.75. It shows it as a good capacitor. This capacitor is most definitely not good. Not when you're putting 150 volts across it. Don't rely on a tester like this for testing higher voltage electrolytics. It turned out that in addition to not having a 1000 microfarad cap on hand, I didn't have a few of the others as well, so I just went ahead and placed an order for all these guys. Now while I'm waiting for that to arrive, which hopefully will be in just 2 or 3 days, I went ahead and unmounted this guy. Now, this schematic's a little unusual, and it doesn't really appear to be a ground. So here's this cap, and the negative lead on that just kind of goes around, and I noticed while looking through this there's no actual ground symbol anywhere, so like the whole thing's kind of floating. So this does not connect to the frame. This is insulated on a phenolic wafer base and has a cardboard cover over it. It's rather easy to get out because of these twist locks. Only one actually had anything attached to it, so I just had to take these flat nose pliers and straighten the other 3 out, unsolder a couple leads from this, straighten that out, popped it right out. Oh, and of course I had to cut these leads out, but only after taking a reference photo and some notes so I can put this back in the right way, rather than having to trace it all the wiring on the schematic. Now, I also got lucky in that this cardboard tube, ta-da! Often I have to heat these up in an oven or with a heat gun, and even then sometimes they just won't come off without falling apart. But if you're lucky, over time this tar has separated and you can just get it like, open like that. So all I'm going to do now is cut this thing open about here, pull the guts out, drill in some holes, mount some new caps, put the cover back on, and remount it and hook up all the wires. There, that was fairly easy. Cut the can open, put out the insides. I drilled a few holes. I went with 2 22 microfarad and 1 47 microfarad, all 105 degrees centigrade Michicans. Remember, 2 of the 22s are bridged externally, so I just ran a single 47 down the inside. Nobody will ever know the difference. And they all fit just inside a little bit of cardboard. Like so. Here's the capacitor remounted back in the chassis. Also went ahead and checked all of the big 2-watt carbon comps, and I'm happy to say that they are all still within specs, so I'm just going to leave them alone. Same is not true for this area. While I was unmounting that big filter cap, I had clipped out some components, so I just went ahead and replaced those. These others were drifting a bit out of spec, so I went ahead and replaced those as well. Now, one confusing thing is that there was another resistor up in here. It's a 220K. This end seemed to be soldered in the same as the others, but the other end, it was just kind of like just shoved in here and soldered. It wasn't wrapped around the lug, and it's not shown on the schematic. So I'm going to leave it out. It was in parallel with the 100K. So the effective resistance with the two together was about 75. I'm going to leave it out and see if this calibrates. What I'm suspecting is that it was added, not only because of the way it was soldered in, but also it had green spaghetti tubing over the leads, whereas everything else in the set was white. So I'm thinking this may have been tacked in place at some point. Maybe because they couldn't get it to calibrate with the components that were in there, but now that I'm replacing faulty capacitors and out-of-spec resistors, maybe it's not needed anymore. Now, something else you may have noticed is that there's some stuff missing. That would be these two guys, which are selenium rectifiers. As these age, the internal resistance goes up. So even though they may be functioning or seeming to function, probably dropping more voltage across them than they were originally designed to. And when these fail, and they will fail eventually, very stinky when that selenium goes up in smoke. So I figured, well, I've got this open, might as well replace them. So this, they're both tapped, meaning that they can be used as one big diode or two smaller diodes. So this was just a single diode. Mounted in here, half-wave rectifier, then replaced with a type 1N4007 diode, rated for 1000 volts peak, inverse voltage, and 1 amp steady state current. So that would be this guy here. And I know it's something that's very commonly discussed in the forums is, should you add a series resistance, and if so, how much, to compensate for the lower internal resistance of a modern silicon diode? Well, I'd say that it depends. Depends on the circuit. For example here, 47 ohm resistor between the rectifier and the first cap. The real reason these are here is not to drop voltage. It's because these cannot take much of a peak current without getting damaged. When this sets off, the capacitors are discharged and then turned on. It's a surge of current because this is acting like a dead short. Without that, it can exceed the current rating of this diode and damage it. Modern silicon diodes can withstand a much higher surge current, but it's not infinite. It's still a good idea to add that resistor. Alright, but should we increase it? Well, look what's after that. 1000 ohm resistor, another 1000 ohm resistor before it goes off to other circuits. So we've already got 2000 ohms of resistance here. Adding a few more ohms here isn't going to make any difference. It's just swamped out by this much larger resistance over here. You might see a typical rule of thumb is to add another 47 ohms here. Compared to that, negligible, just a few percent, so didn't even bother. And similar logic over here. Just left the same 47K. I could have gone up to maybe 100K, 82 ohms. I should say 100 ohms or 82 ohms or 68 ohms, but they had 47s in there originally. I just put 47s in there, so hopefully if anybody ever works on this in the future, it's going to match the schematic. There won't be any extra components added in, so as to minimize the confusion. And well, that's really all the work I can do. I replaced the one paper cap. Electrolytics should arrive tomorrow, and then I can finish this off. Got 1, 2, 3, 4, and the 2 I clipped out. Six caps left to replace.